Hello students and welcome to this video lesson. Today we're going to be learning about coordinate proofs by using slopes and lengths and then applying our understanding of the properties of quadrilaterals. On page 20 in your packets you'll see this big table. We're actually going to skip it today just because I'm not there. But we will resume and do this table eventually. This is basically a good study strategy for understanding how all the shapes correspond to one another. We will fill out this flow chart though, so I believe this is on the next page in your packet. So if you take a moment and pause the video, I'd like you to copy this in. When you're done copying, let's talk about what it means. So this is kind of like the examples I've been using in class where I talk about a family tree. So the way it works is we have the big subcategory of quadrilaterals, so all four-sided figures. Quadrilaterals can be separated into three distinct families. We have kites, trapezoids, and parallelograms. The definition of a kite is that it has no parallel sides. A trapezoid has one set, and a parallelogram has two sets. So that's why they're three distinct families. Now the kites, there are no other shapes that really have no parallel, so kites are the bachelor of this family tree. We have trapezoids, and trapezoids ended up having a child. It's a isosceles trapezoid, so it has all the qualities of the trapezoid, but it has something extra that adds into making it an isosceles. The parallelogram has two separate children, the rectangle and the rhombus, and then if the rectangle and rhombus got together and had a baby, it would have a square, because what it is the square has the property of all of the shapes up here. So it's a family lineage, like I say down here, where the square possesses all the qualities of the shapes above it within that family. So same thing, isosceles trapezoids possess all the qualities of a trapezoid, and then some extra as well. So again, this is really important to understand the relationships between the shapes, and that's what we're really getting into today. So what's it going to look like today? Well, today we're going to put all of these quadrilaterals on the coordinate plane. And I'm just going to basically ask you, what shape is it? Now, a lot of the times when you look at the picture, it'll be really obvious, okay? So it says, determine whether this one's a parallelogram. Pretty sure it looks like a parallelogram, but the justification is the important part. So there's a bunch of different ways you can justify mathematically that this is a parallelogram. So, okay, we answered this question. It looks like a parallelogram. Yeah. Okay. How do we know for sure? That's what we're getting to. So these are the four different options, and I believe there's a place for you to copy this into your notes packet. First, you could show that opposite sides are parallel, or you could show opposite sides are congruent, or you could show the diagonals bisect each other, because again, that's only true in the parallelogram family. Or you could prove that opposite angles are congruent and consecutive angles are supplementary. Okay, that's a lot. Okay, so on each problem, you're going to want to just pick one of those. So on this one, I have decided I would like to prove opposite sides are parallel. You could have totally chosen a different one, but this is what I'm going to go with on this example. Well, I know to prove things are parallel, I need to calculate the slopes. And if they're parallel, they will have the same slope. So all I'm going to do is count rise and run. There's no actual formulas or anything here, just count up and count over. So if I do this, I'll do it in a pretty color. Let's do this blue color. So J to M. So J to M has a rise of 2 and a run of 3. So the slope is 2/3. Now, without too much math involved, I could do the exact thing over here. L to K, or K to L, it says. The rise is 2, the run is 3, the slope is 2/3. Okay, I'll do the other ones really quickly. J to K. Let's see. Oh, we want a different color. We'll do green. J to K is here to here. So the rise is 3, and the run is 8, I believe. And it is a negative slope because it's going down, so I believe the slope is negative 3/8. If I count again, L to M or M to L, I go down 3 over 8. Yep, it's negative 3/8. So, well, does that prove it's a parallelogram? Yes. It means JM and KL are parallel, since they have the same slope, and JK and ML are parallel, because they have the same slope. Therefore, JKLM is a parallelogram. What you just did is called a coordinate proof. So now we're just going to practice it a bunch more. There we go. All right, next one. We have a quadrilateral with these four corners. Use the side lengths to determine whether it's a parallelogram. So again, this time I'm making you try to show that opposite sides are congruent. Okay, again, that's just one of the options, but that's the one I want you to use this time. So in order to do that, we need to actually do the Pythagorean theorem or the distance formula. So I like to call it the Pythagorean theorem because distance formula usually has that big square root thing in it, and I'll kind of show you what I'm thinking. So first off, you're going to want to plot the points. So I plotted all 4 points over here. And I actually like to always connect them as well, because then I can see if it does in fact look like that shape. Oh, I guess we're still on green here. Being festive here. Okay, so I look at it and like, yeah, it looks like a parallelogram. Let's see. So I'm going to draw in my little triangles. Oopsies. So let's do K to L first. So K to L, basically I'm making this little right triangle here in blue, and I'm counting the sides. Well, this side is 1, and this side is 6. So all I'm going to do is 1 squared plus 6 squared equals c squared. I already did that over here. I get 1 plus 36 is 37. And so the length of K to L is the square root of 37. Now the cool thing is you do not need to grab a calculator. You can just say the distance is the square root of 37. That is good enough for me. I don't actually care what the decimal approximation is. All right, let's do the other 3 as well. Well, actually, if I count this one is 6 and 1 as well. Do you see that? So I don't need to do Pythagorean theorem all over again because I know if I have 6 and 1, same thing as 1 and 6, I'm going to get 1 squared plus 6 squared, 1 plus 36 is 37. So actually, this one's square root of 37 without doing any math. Okay, if I do the next one, I'll see it's 1 down, 3 over, or excuse me, 6 over. So it's the exact same formula. So that one is also the square root, oopsies, there it is, the square root of 37. And I have a bad feeling about this. 6 and 1, same thing. It's going to be the same answer. So the question was, is this a parallelogram? Well, yes, it is. But actually, it's a terrible question because actually what it is it's a rhombus. But it still is a parallelogram because opposite sides are in fact congruent. I just actually have an extra thing that all the sides are congruent. So this is just a terrible question, so I apologize. So the conclusion is we know that KL and MN are equal, and LM and NK are equal. So the opposite sides are in fact congruent. It proves it's a parallelogram. Nice. Alright, so my packet has one more parallelogram example. Here are the 4 coordinates, and it says I can use any technique I want. So there were 4 different ones, I believe, but just because it's a lesson, I'm going to ask you to do this one. Find the midpoint of FH and GH. So why would I make you do that? Well, first off, I started by plotting the points. If I draw the diagonals in and find the middle of that one and the middle of that one, if I'm able to prove that they have the same midpoint, what that tells me is that these segments are bisected. And that parallelogram family, again, is the only one where both diagonals bisect one another. So that is a way to prove it. Most people don't choose this way. Most people either do the distance formula or the slopes. But I do want to throw it out there as an option. Now, when I look at this picture, I think it's pretty obvious, but I'm going to do the midpoint formula just in case. Midpoint formula is where you add the 2 x's, divide by 2, add the 2 y's, divide by 2. So I did that ahead of time. So, oops, there it is. The first one I did, I just realized that is a typo. That should say, hold on. Oh, okay, sorry. I figured out what my typo was. I put H and J in the wrong spots on my graph. So, apologize about that. Oopsies. Alright, there it is. Okay, so now I did in fact find the middle of F to H. It ends up being 0, 0.5. And same thing for G to H. I did the same thing, found the middle. It is in fact the same. So again, what that means is the diagonals have the same midpoint. which means the diagonals are bisecting of each other, and therefore it is a parallelogram. So just throwing it out there. You do not have to use this property. It's just another option. Okay, so that was enough about parallelograms. Let's talk about all the other shapes. So we're going to focus on rectangles, rhombi, and square today. Here are the different ways that I would suggest proving that it is a shape using our coordinate graphs. So in a rectangle, you can either prove the diagonals are congruent, or you could prove consecutive sides are perpendicular. A rhombus, prove the sides are congruent, or prove the diagonals are perpendicular. The square is an and one that is important. You have to prove two things. So it's twice as much work to do squares. You need to prove all the sides are the same, and you get 90-degree angles. So the consecutive sides are perpendicular. So again, I believe you have a spot for this in your notes. Make sure to copy it in. All right, so let's try one with these other shapes. It says Mr. Scardigley calculated all the slopes and lengths of the sides and diagonals of the quadrilateral below. He determined the most specific name for it. Is it a parallelogram? Is he correct? Well, it does in fact look like a parallelogram, but that's not mathematically sound. So let's see here. We got some slopes, 6, 7, 6, 7, negative 2 9s, negative 2 9s. Well, that right off the bat tells me these are parallel, and these are parallel. So that's good. That's a good start. But one thing I noticed that's kind of particular is these slopes. These slopes are opposite reciprocals of each other. So in other words, if I connected A to D, or excuse me, A to C, and B to D, they make a 90-degree angle. Well, that's not true in parallelograms. That's true in squares or rhombi. Well, this is clearly not a square, right? If it was a square, these would be opposite reciprocals. So maybe it's a rhombus. Well, let's look here. It says all the lengths of the sides are 9.22. Well, that for sure tells me that this is a rhombus. So there's two defining characteristics. I would probably pick the side ones because that's the most obvious. But these are in fact all the same because they are all 9.22. So he's wrong. It is a rhombus. Let's do another one. Alright, here's another quadrilateral. Determine if it's a rectangle. So I'm giving you a heads up on here's what I think it is, but we got to prove it. So the first things first, you're going to draw all the graphs, or all the coordinates on the graph. And I'm going to look at it and say, yeah, I'm thinking it looks like a rectangle. Well, there were two ways to prove rectangles. One was doing diagonals, and the other was trying to prove 90-degree angles. I'm not a huge fan of the diagonals, so I'm thinking I'd rather just calculate the slope of each side. If I can prove that the slopes of the ones next to each other are opposite reciprocals, that would prove they're 90 degrees, and that would therefore would prove it's a rectangle. So I'm just going to calculate the slopes. So P to Q is my first one. Rise and run. Let's see. The rise is 4 and the run is 6. And it's negative because it's going down. And you're going to ask, do I need to simplify? Yes, you do. And you'll see why in just a second. So that one's negative 2/3. S to R is also negative 2/3. Q to R is, let's see here, up 3/2 positive, so 3/2. S to P is the same. So you'll see why I had to simplify is otherwise you would not see this opposite reciprocal relationship without the simplified because I see 3/2 and negative 2/3. Those are in fact opposite reciprocals of one another. Therefore, it proves that it is a rectangle. So here's a little explanation I wrote up. I said the slopes of the opposite sides are the same, negative 2/3, negative 2/3, which means the opposite sides are parallel. That for sure means it's a parallelogram. And then to further it, the consecutive sides have opposite reciprocal slopes, which means they're perpendicular, therefore it is a rectangle. Alright, I think we have only one more. This is the success criteria, yes. So this one I don't give you any hints because it's the hardest one. And it says it could be any of the 4 shapes we know. Let's figure it out. So you're going to plot the points. And again, I like to connect the dots and see if it in fact looks like something obvious or not. Alright, so I'm looking at it and I'm thinking probably not a rectangle, probably not a square. I'm a little conflicted if it is a rhombus versus a parallelogram. So in that case, I know a rhombus has to have all congruent sides. So I think I want to calculate side length opposed to slope this time. Because slopes wouldn't tell me if all the sides are the same. They would for sure tell me if it's a parallelogram, but I wouldn't be able to make that distinction between the two. So I'm going to get out my handy dandy fun colors. Let's do pink this time and get started. So if I draw my triangle in, I have a rise of 6 and a run of 7, but I'm using Pythagorean theorem, so I'm going to go, I lost my work. I found it though. I'm going to go, nope, it's not 2 plus 9. It is, hold on. Okay, I found it. So there it is. 6 squared plus 7 squared. 36 plus 49 is the square root of 85. So j to k is the square root of 85. Alright, I know I kind of ruined it here. So next up, purple. K to L. So it is how far over, how far down, 2 and 9. Oh, hey, look, that's right here. 2 squared plus 9 squared actually ends up also giving me the square root of 85. So K to L is the square root of 85. Now I'm just going to save you the time and effort. LM is also 6 and 7, and MJ is also 2 and 9. So it ends up being that they're all the square root of 85. So what does that tell me? What shape is this? Well, it's clearly a rhombus because all of the sides are congruent. All right, so I know that was a pretty long lesson. Make sure you have all that copied in your notes, and I believe there's 2 pages of homework today. I want to say it's pages 24 and 25, but don't hold me to that. So get working on those coordinate proofs, and good night.